promise for advancements that we can only begin to imagine. The transition from classical to quantum physics was not a smooth one. It involved a radical shift in thinking, a complete overhaul of the way we view the universe and our place within it. Classical physics, with its deterministic laws and predictable outcomes, had reigned supreme for centuries. The universe was seen as a giant clockwork mechanism, its future predetermined by its present state. However, by the late 19th and early 20th centuries, cracks began to appear in this seemingly perfect edifice. Experiments at the atomic level yielded results that defied classical explanations. Light, for example, sometimes behaved like a wave, spreading out like ripples on a pond, while at other times, it acted like a particle, a discrete packet of energy. These experimental anomalies forced physicists to rethink their fundamental assumptions about the nature of reality. The quantum revolution had begun, ushering in an era of unprecedented scientific exploration and discovery. The pioneers of quantum mechanics, giants like Niels Bohr, Erwin Schrödinger, Werner Heisenberg, and Max Planck, developed a new set of rules to govern this strange microscopic realm, rules that often seem to contradict common sense and defy our everyday experience. This paradigm shift in physics had profound implications not just for our understanding of the physical world, but also for our philosophical outlook. The deterministic clockwork universe of classical physics gave way to a more probabilistic, uncertain view of reality, where the future was no longer predetermined, but existed as a superposition of possibilities. Perhaps no single experiment better illustrates the strangeness of the quantum world than the double-slit experiment. This experiment has fascinated scientists and laypeople alike for over a century, challenging our understanding of reality itself. This deceptively simple experiment, first performed with light in the early 19th century and later repeated with electrons and other particles, has become a cornerstone of quantum mechanics. It demonstrates the wave-particle duality of matter and the profoundly counterintuitive nature of the quantum realm. The implications of this experiment have led to numerous advancements in quantum theory and technology. Imagine shining a beam of light at a barrier with two narrow slits cut into it. This setup might seem straightforward, but it holds the key to understanding some of the most perplexing aspects of quantum physics. Behind the barrier is a screen that records where the light hits. This screen acts as our canvas, capturing the behavior of light as it passes through the slits. In the classical world, we would expect to see two bright bands on the screen, corresponding to the light passing through the two slits. This is what our intuition in classical physics would predict. However, what we actually observe is a much more intriguing pattern, an interference pattern of alternating bright and dark bands, as if the light waves passing through the two slits are interfering with each other. This pattern is reminiscent of waves in water, where peaks and troughs interact to create a complex pattern. This interference pattern is a clear indication that light is behaving like a wave, spreading out and interfering with itself. This wave-like behavior of light was one of the first clues that the quantum world operates differently from our everyday experiences. However, if we dim the light source so that only one photon, a single particle of light, is passing through the apparatus at a time, something even stranger occurs. This setup allows us to probe deeper into the nature of light and matter. Even though there is only one photon, the interference pattern persists, suggesting that the single photon is somehow interfering with itself. This phenomenon defies classical logic and suggests that particles can exhibit wave-like properties even when isolated. The double-slit experiment highlights the wave-particle duality of matter, one of the central tenets of quantum mechanics, which states that particles can exhibit both wave-like and particle-like properties. This duality is not just limited to light but extends to all particles, including electrons and even larger molecules. It also introduces the concept of superposition, where a single particle can exist in multiple states simultaneously, passing through both slits at once, even though it is only a single entity. This idea of superposition is fundamental to quantum mechanics and has profound implications for our understanding of reality, leading to the development of technologies like quantum computing and quantum cryptography. Superposition and entanglement are two of the most mind-boggling concepts in quantum mechanics, challenging our classical intuitions about the nature of reality. These phenomena defy our everyday experiences and force us to rethink the very fabric of the universe. Superposition, as we saw in the double-slit experiment, is the ability of a quantum system, such as an electron or a photon, to exist in multiple states simultaneously. This means that a particle can be in different places or have different properties all at the same time. It's like a coin spinning in the air before landing on heads or tails. It's in a superposition of both states until a measurement is made. This analogy helps us grasp the concept, but the reality is even stranger, as the particle doesn't just have two states but can exist in a complex combination of many states. Entanglement, on the other hand, is a bizarre connection that can exist between two or more quantum systems, even when separated by vast distances. When particles become entangled, their properties become linked in such a way that the state of one particle instantly influences the state of the other, regardless of the distance between them. Imagine two coins, each in a superposition of heads and tails, but linked in such a way that if one coin lands on heads, the other coin instantly knows to land on tails, no matter how far apart they are. This instantaneous connection defies our classical understanding of space and time. This spooky action at a distance, as Einstein famously called it, has been experimentally verified and remains one of the most perplexing aspects of quantum mechanics. Despite Einstein's skepticism, numerous experiments have confirmed that entanglement is a real and fundamental feature of the quantum world. These strange quantum phenomena are not just theoretical curiosities, they have the potential to revolutionize various fields. From secure communication systems to ultra-precise sensors, the applications of quantum mechanics are vast and varied. Quantum computers, for example, exploit superposition and entanglement to perform computations that are impossible for classical computers, potentially leading to breakthroughs in medicine, material science, and artificial intelligence. These machines can solve complex problems at unprecedented speeds, opening up new possibilities for innovation and discovery. Understanding and harnessing these bizarre quantum effects is one of the key challenges and opportunities in modern physics. Researchers around the world are working tirelessly to unlock the secrets of the quantum realm, aiming to develop new technologies that could transform our lives. As we delve deeper into the quantum world, we are likely to uncover even more counterintuitive and potentially transformative phenomena that could reshape our understanding of the universe and our place within it. The journey into the quantum frontier is just beginning, and the discoveries we make could redefine the boundaries of science and technology for generations to come. Thank you for joining me on this journey into quantum mechanics. If you enjoyed this video, don't forget to like, subscribe, and share it with others who might be curious about the quantum world. And as always, stay curious. Hebrews 11:3. By faith we understand that the universe was created by the word of God, so that what is seen was not made out of things that are visible.